All right, welcome back, everyone. And now we're going to continue more on our IK rig system. In the previous video, we started doing with inverse kinematics. We went through the FABIK algorithm, how to apply it. So we're going to take the concepts of Fab and just throw a whole loads of math. Now, instead of just moving points to where we were guessing, just like how Fab does it, we're going to actually start doing. We're going to use some algorithms. We're going to use curve algorithms, and other things to really apply it, because the way Ubisoft does it is kind of a different approach. Granted, I don't know how they exactly do it. I only can know how much they kind of demonstrate in their video. So, speaking of, this is the GDC video that I'm using that I've watched several times to try to figure out what they're doing. And the way they're doing it is where they have, like, let's say, in the point of a leg, they define their data not as like a bunch of points, more as here's my hip, here's where the foot needs to be. That's it. And then where's the forward direction? And and then from those two bits of information, they're able to calculate where and how to bend the elbow, or how to bend the knee and everything else. You know, that's really the gist of it. Now, you might look at this, okay, whoop-de-doo, but there's something magical about the way their approach is, which I think, that took me a while to try to figure out. It took me actually days, and this video is going to become a little bit math heavy. I'm not fully understanding of the math, even though I wrote it, but like I just kept hammering away at it until I got it working. As you can see how it works, it's just changing that end position where you want to go, and that forward direction kind of dictates where the knee needs to go. But in a second, he'll show you the beauty of having that very simplistic bit of data, because now we're just dealing with just two joints, really, and the foot basically goes in the parallel direction of the normal of the place you're going to. So if you're touching the floor and the normal direction is up, and you kind of just rotate by 9 degrees, and that's where the foot goes. But like I said, the foot is based on where it lands, else it animates in its own way. But when it comes to the entire leg, it only animates based on these two positions. Like I said, this position is kind of static. This one's the one that's kind of constantly moving, so it's kind of like just a rotating arc. And and when this thing rotates an arc, you kind of have the forward direction anyway, because it's kind of like parallel or perpendicular to this line. I'm going to use the word correctly, perpendicular. I was waiting for it. I thought I had it further enough. There you go. Oops, I don't want to. Now, here's like I say, here's the beauty of the algorithm he's using. See how it uses a two-joint thing, a two-joint leg, and it maps it correctly. And it has a three-joint leg, and it is used in every single leg uses the exact same data. It's just that video, that line and the arrow they were showing. It's the exact same data. By what he said, it's how they animate, and then they just apply it to any rig they want. So you can have one leg animation that works for all these types of legs. You know, this is a regular leg. This is an animal leg. This is something something mechanical. There's an octopus leg, and here's more piston type of leg. It just, if you look at this leg, it has no rotation at all. It's just that distance, and the foot all placed in the same way. But and here, like I said, that's the beauty of it. It's so simple to have this bit of information, just this direction, just like two directions basically, and move all these joints in all these different ways. Like this one has like no rotation. This has a lot of rotation. It does a curvature, and this is what really took me days to figure out, how do I get this just right. And so yeah, I managed to kind of come up with some solutions to actually solve some of these issues. Like I can get this leg going, and I can get this leg going. Maybe this as well. This is like a sine wave. It just follows the sine wave. But I don't use the sine wave either. I use I have like several. Here's the thing. I actually have other solutions for things that aren't even here just because I just walked into them. There are just a lot of failed attempts of different approaches till I found an approach that got to work. But some of those failed attempts, some of those failed approaches that didn't get the end result I wanted, I'm still keeping because they create something unique and different. And I'll kind of go through some of it today. So the one thing I realized that for like mathematical wise, this requires a lot more math. Depending on which algorithm you use or which curve algorithm you use, it requires a lot more math. But a two joint leg and an arm requires very, very little math. By using that simple amount of data, it takes a lot of math. So I actually end up creating different functions. So if your chain only has 2 joints, do this basically. If you're I don't have anything for 3 joints yet, but maybe the sine wave will work for it. I'm not sure. But if you have 3 joints, do this. If you have more than 3 joints, do this one. I think that's my approach for the IK system. So it's not a one size fits all. Even though you have one bit of data, just to optimize things, I decided to essentially I could use this curve one with this leg, but it ends up being a waste because it's so much math that goes into it. So it's a lot simpler. I figured out some very simple math to get this one working. So having that one bit of data to use and then just have different functions that interprets it based on the amount of joints will optimize it as much as possible. So you're not trying to do an octopus type of tentacle leg when a human leg will suffice. You don't need all the curvatures and all that, and all the things. So I'm gonna go talk about the human leg first, and because in an RK rig, if we're manipulating a human, the arms and the legs are all completely 2 joints. So the math is actually quite simple. The only thing that we might need more advanced things for is maybe the spine, because the spine can be sometimes between 3 to 4 bones, depending on how your armature is set up. So the way I approach the legs and arms, so you have this, right? So here's our starting point. This is our hip. Let's say this is the start of our leg, and this is where we want to be. So we have a specific length. And just like I said, when it comes to IK, if this length exceeds the length of the chain of all the joints, you straighten out the leg. You're done. You don't need to do anything. There's no calculations need to do. If it exceeds, you automatically straighten out the leg, or you straighten out that chain of joints. If it's less than the length, then you start applying some kind of algorithm to it. So normally in inverse kinematics, we kind of just work backwards. But for this one, we don't need to work backwards at all. We can actually calculate where the midpoint is, and we can get it very accurate, which is beautiful. That's the best part, is we can get it accurate. We don't have to run, like in the previous video I showed you, I had to run it like 4 times before the arm was a 3-joint arm, but it took 3 or 4 attempts for it perfectly touching the endpoint. For a 2-point, it's very simple. So we know it's going to be short, and we know there's a couple of things we know. We know the length between the start and end point, right? And we know the length of every bone, right? So we know the length of the bone. Every bone, so here's bone 1, bone 2, here's our knee, and there you go. So what does that look to you? That looks like a triangle. Now, you can solve and what we only need to do is figure out what is the angle that this leg needs to turn for everything to kind of like basically because we're going to use our inverse kinematics, like the forward kinematics, and we just get into a target. So we need to know where this knee is, because we know where the foot's supposed to be. We know where the hip is supposed to be. We need to solve where the knee is. So to solve for the knee, we need to know the angle of this part of the triangle. I think it's someone suggested because I was having problems trying to solve triangles, and they said like, how do I solve something if I only know like two lengths or something and one angle? In this example, it's not that, but they said the law of cosines, the law of sines to solve that. When I was studying, looking up how to do this, the law of sines, I saw the law of cosines, and the law of cosines can actually help us with this solution. Because I did this one last. I did the tentacle first, and then at the very end I did this one. So by that point, I already went through like 3 or 4 days of a lot of geometry, triangle things, just smashing my head against the table until I got it. But one of the law of cosines is if you know the lengths of every like part of the triangle, like every side of the triangle. So that's, let's say that's C. I think the example I saw was B, and this is A. If you know all the lengths, then you can. There's an equation to solve basically every angle. And since I only care about this angle, this is considered angle A because it's the opposite of angle B. You know, that's angle C, and that's angle B. And this becomes kind of important because we do use more of this, and later on in the video when we're dealing with other algorithms, because this essentially, like, I end up doing it backwards. I end up doing everything complicated, and then at the very end I did something simple, which if I did something simple and worked myself up, I probably wouldn't have taken me 3 or 4 days. But that's the idea. We're going to use the law of cosines to calculate the angle. Because if we know like I said, it's a triangle. Everything's a triangle. So if this length is less than the total length of these two together, that means it's not a straight line. That means these two will have their actual length. And like I said, since we know the 3 lengths of the triangle, it's very easy to figure out the angle. So once we figure out the angle, we can then calculate this target position, then just apply it to our forward kinematics, and it makes a perfect connection in one go. We don't have to move things around. We don't have to calculate the lengths from endpoint to endpoint. It's actually a much quicker algorithm than FABIK, the inverse kinematics function. So let me just show you kind of where we left off in the last function last time. I cleaned things up a bit. I have created a class called Kinematics. Backwards is the old function that we used in the last video to perform the inverse part. I call it backwards projection. It's just the basic inverse kinematics that we can use. And then we apply projected points. It's the same function. The only difference is that I keep track of world and local in this function instead of applying it back to armature. So this way I can do all the math without actually moving the armature, because I want to be able to make keyframes, and then use those keyframes to modify the armature. So I'm actually trying to pull out of that out. So this is the only change added, like this part too, where I'm actually keeping track of all the transform hierarchy. So that's one of the big changes really to it. And if I were to show you, and this is, like I said, I'm starting off with 8 points, and this is our inverse kinematics, just fixed up a little bit and cleaned up. The naming conventions are a little better, and here you go. It does a pretty good job. It does not disappoint. So now we need to go switching over to doing elbow joints and knee joints. So let's move it to 2, and we're going to get rid of our basic FABIK, and we're going to apply our 2 joints. So we're going to use our 2 joints. Oh my god! Click refresh, and there you go. Very simple. Now, in this example, the two joints are the exact same length. So there's actually another way to actually solve it. But joints can be any size, so I had to make sure the algorithm works. So just to make sure, like to prove that point, I had this little bit where for every time I create a new joint, it resizes everything. So if I click refresh, did I do it correctly? Times I plus 1. Oh, wait a minute. Oops, I put it in the wrong position. Right here. Oh my god, I keep going back to that one. Refresh. There we go. As you can see, even though the bones are now different sizes, everything is still a triangle, and it solves it in one go by using the law of cosines to actually calculate this angle right here. So this, once I know that angle, everything kind of just falls into place because that's geometry. I believe it's geometry. So let me take that out. So like I said, I had to make sure that that works because all bones need to be treated differently. And like I said, here's the equation for the law of cosines. It's like the length b squared, the length of b squared, the length of c squared minus the length a squared. A is the opposite. So like I said, if this is the opposite, this is what I need to subtract because I want to get that angle. It's the opposite. Like you can rewrite all the everything over again. Where if I need to solve for b, I subtract the b length. If I need to solve this one, I subtract c. So you can rewrite this function over again just by swapping things out. So this is the law of cosines to solve for the angle of A. And like I said, it's and the only thing I have to do is copy this over to here, really. And say arc. So that's really the actual equation at the very end, because even though all this equals cosine of A, I need to know the angle. So to get the actual angle, I need to say arc. So that's why I have math.arc cosine here with the entire equation put to place. Then I use a function that I have, which allows me to basically define a plane, a circle in 3D plane. You'll see this a lot more in the video about constraints. One video from now, or next video, because I did all this in one go. So, so I use this to really just help me calculate in 3D space the position of a circle, and it doesn't matter which plane it is. And the only caveat here is that this chain function that I haven't really explained yet, which I use a lot. I'm going to use. It's very important because I need to know a certain axis. So, but like I said, this helps me calculate all the angle, find the angle, and this finally lets me take that angle and then figure out the actual position in world space. Now, I guess I can show you that function because I think I've never shown it before. I threw it inside the maths. And it's a plane circle and plane ellipse. Very simple. Now the interesting thing is that you need to pass in a center point, which it can be just 0, 0, 0, but it's just, a plane is defined by a point and a direction, and all you need to do is pass in where you consider the x-axis to be and the y-axis to be of that plane, and you have the center point, and then you can then apply a circle in 3D built perfectly. So before in videos, when I had to create a circle, I had to create a circle and then rotate it. Now I can actually create that circle in that specific plane without any rotation at all. Basically, the rotation done here already using cosine and sine. And I actually modified this function to allow me to do an ellipse as well. So, it's just the only difference is you add in a y radius, and then I just pop it in the right spot, and you can create ellipses in 3D space. So this is the math.js file. If you want this function, like it took me forever to find the math example of this, and it's very useful. If it wasn't, this makes certain things a lot easier. So now the last thing to really, like I said, this is all the math, this is all the code that actually gets that one point, and then once I have that point and the end point, so like I say, I have the target, or I calculate where the elbow needs to be, and then the end point, and then I use forward kinematics to actually retarget everything, and it does a perfect job in one go. It's like so it's actually might be more efficient than using Fab if you're only dealing with 2 joints. Like I keep in mind, like I said, it has to be different for a certain amount. The amount of joints dictates which algorithm I'm using. So this is the 2-joint algorithm. Very simple, just a triangle. And the kinematics chain line, which is kind of important, which is important for everything. All it does is define information of that line. Oh my God. Like I mark it here with the red line. Let me go up here and let me change. So I can change the endpoint all I want. Let me see. Let me just move the endpoint there. And see, like I said, it does a perfect job of it. It's like that's the endpoint, and that's it. And it figures out, it calculates exactly where it is, and then when it does the retargeting, it hits spot on. Geometry is so fucking awesome, right? I haven't touched geometry in really sat down and really sat there and really tried to do geometry in like 15, 20 years. But here you go. I'm learning it. I'm relearning it essentially, and it's doing an awesome job. So now I totally lost track of my train of thought because I'm living math so much nowadays. Once I figure it out. So what was I looking at? Oh, that's right. The definition of the line. So like I said, in the IK guy, you have that. So we know that line. That's our line, and we need to figure that out. So the whole point of this function is to figure out all the information about that line specifically. So I know I pass in the chain, so I figure out where the world position is of the start. So the chain where it exists, its world position. So I know where everything starts. The endpoint is our target, so that's our endpoint. And I create a new vector because I don't want to accidentally modify it because everything passed in by references. So I need to create a new vector 3, so I can do things with it and not this actually doesn't screw anything up for me. So I end up then on top of that, we need the length, the vector length. So I need the direction that I'm going from start to end. So a start to end length. And I mark it with a V so I know it's the vector length. And then I do the actual length of it because I need to know its actual length. And if its length is greater than, I probably should use square. I probably fix this up to be square length. And then if I need it further, then use square root of it. Like there's a little bit more optimization I can do here. But if the length of that line exceeds or equal to that length, it's too far. That means just straighten out your chain. Just straighten it out and rotate. So I haven't. So every once in a while, if I move a point around, the entire thing crashes because I'm not doing anything with it. But like I said, it's a to-do. So now one of the things I need, since I need to figure out these triangles and these circles, like I'm kind of converting everything to vector math. I need to know the axis of things, especially since I need to know where the forward direction is. So I'm using this line. So I'm taking that line that from the start of our chain to where we want to go with our chain. I'm using that as the x-axis. So if that's my x-axis, I use that to help calculate the x-axis. And then from there, I just take this and take the x-axis, normalize it so I can create the y-axis. and then from there is the Z. Actually, the direction is actually Z. So so the direction that I'm going this way, I'm considering the forward direction. That's the forward direction for this chain. And I save all that information here. So start, end, as that, and that. And if I know where if that's my forward direction, then I know where my up direction is. And that's why that point is there, because like I said, when he oh my God. Because like I said, this is my forward direction, and I'm calculating the y-axis. This is my y-axis. So I know exactly where to push it. This function probably needs more work. Like I probably need to pass in a forward direction, so this way I can always put the elbow or the knee where I need to go. But like I said, I'm still trying to figure a lot of those pieces out. So I'm just letting everything just flow where they're going to go for now, and then later on I'll be more specific of where I want everything to go. So I'm just taking that forward direction and then using the up direction to help me figure just ideally where the y direction is going to be going, where the elbow or where the knee is going to go. And by knowing that information, I'm able to use the z-axis and the y-axis to kind of calculate where in the circle that everything needs to go. And that is essentially the two-joint thing. That's simple. If you only care about that, go for it. You can leave now. Now I'm probably going to start going to more complicated stuff. All right, so let me go back, and I got like a couple algorithms, but I don't want to go through every single one. So leave that there. Now we're going to do something called the catenary curve. The catenary curve was a pain in the butt. This is the one that actually works really well for tentacles, for them, kind of. This one was kind of really pain in the butt to find source code for. Like this is the easy part. Like this is the catenary curve. That's it. That's all really. That's all it is to it. The biggest problem is solving A. What a catenary curve is it's a parabolic curve, but it's not any kind of parabolic curve. It's the parabolic curve that you can use to calculate the hanging of a chain. So if you have like a rope or chain, so if you have like rope and chain between 2 points, and you have that curvature, it can this algorithm can actually calculate that specific parabolic curve of a hanging rope or hanging chain. If they're perfectly even, then the end results that you get is that, and you get that perfect parabolic kind of curve. But the thing that's really important with the catenary curve and why this one works so well is that the further you stretch it out, the lower the curve, to the point that when you stretch it out to past the maximum length, it becomes a straight line, because it's like I said, it's a curve for rope and chains, or like any kind of thing. So the closer the rope is, you get that weird curvature, to the point like when it gets close to it, when like the two ends get close, it becomes like a straight line. And you're going to see that when you start applying the catenary curve. But yeah, it took me a while to find a decent example of this, and this is an example from I think this link, and I optimized it and I converted to, I don't know if this is in JavaScript or not. Probably not in JavaScript, but I probably converted it into JavaScript and then optimized it. I think I have the original. The first version I did is here. It's a little bit more complicated. I optimized a little bit, and then I optimized. There's some things in here I noticed that I don't even need. So I actually managed to cut down the equation by a bit. Like all of this, I was able to take out. I didn't need to use square root or anything. So yeah, I optimized it, but in case I make a mistake, I have the original function that I wrote here, and the link to the original function of solving for A. So solving for A is kind of the hardest thing. I don't fully understand it. It uses a special algorithm. It tries to find the lowest point on the curve, so this way it can determine how far it goes, like how far, basically how much slack is left. That's what it kind of calculates, how much slack is left in the rope based on the two ends, the distance between the two ends of the rope. So that's the catenary curve. And it works really great for what we want, like if we were trying to create a tentacle or an arm, and we have a certain length, if it's past that length, it becomes a straight line. If it's light, we get that slack. So this way it allows us to kind of calculate almost perfectly every position or every target for every bone, because it does that curve perfectly. So if I do the catenary curve, click save. Let me go to, here's the catenary curve. It's not that long. Some of it is a lot of debugging code. Anytime any part you kind of see DVO is a debugging line, so I can visually see everything. But essentially, in this one I'm going forwards. Oh, that's right. This the catenary curve. I try going backwards, like starting from the end to the back. That doesn't work very well. Going from the back to the front doesn't work very well. So this algorithm, I figured out that if I go from the two ends to the middle, I can then evenly distribute all the joints across the curve perfectly. So that's what the algorithm here is doing that I wrote. So so where I think that I is the end. No, I is the start, right? I can't remember now. I equals. Oh, okay. Now, okay. I know. So I'm just going forward in a direction, and then double I is I'm just going forward in one direction, from 0 to curve count. How many points in the joints I'm doing? Here I'm calculating where I should be. So, like I said, I want to do half and half. So I first, I do by, like, if it's less than midpoint, I'm going to go from 0 to half, or 1 minus half, which is, because this is less than, so it's, let's say there's 6, and the midpoint is 3. So here is between 0 and 2. If I'm over that, while it's under the midpoint, once I'm at that midpoint, I'm going to flip it around. I'm going to go from 6 to 3. So it took me a while to figure out a good, pretty simple algorithm to kind of basically, with one loop, go from two ends. Originally I tried 2 for loops, and I did the first half, then I did the second half, and then I had to duplicate all this code. So I managed to actually combine everything by having a loop go from the first half, and then once you reach the midpoint, it actually goes to the end and then works itself back. So that's what this algorithm, this little bit of math here, does. It allows me to go from 0 to 2, then 6 to 3. And it actually works pretty well. So to make the catenary curve work correctly in IK in an IK setup, you can't go forwards and back. You actually have to do both at the exact same time. You got to go forward and back and meet in the center. So that's what a lot of this, and then everything else is just calculating the target points on the curve, and you'll see it when once I render it. If I click here, refresh, and here you go. So there's the endpoint. The gray dots are the points on the catenary curve, and the black dots are where I eventually have to place it. So I'm doing forward kinematics on it. So like I said, these are all the targets on the catenary curve, and then once I pass those points in, I do forward kinematics and target, and everything, and it really hits the point just right. Most of the time it actually hits the spot just right. Other times it might miss it by a little bit, but not by much. If I can probably do one more inverse kinematic step on it, just to move it, just to nudge everything a little bit closer if I really care about it. But yeah, that's that's it. And like I say, and it works pretty well. I can let's see, let me move this up. And like I said, this is let me just do the slack. So let me take away some of the slack. And there you go. See, now the 2 points are small, so now it kind of overshot it. Like I said, it's almost perfect. It's not perfectly perfect, but like I said, if I were to do the inverse kinematics like projection and just shift everything over just a little bit, it'll fix the problem right away. Like I said, I made this nice overarching reach. So if I want to have like a tentacle monster, this algorithm allows me to do it. So like I said, there's more slack. So if you think about this, can I do it? I don't think the camera lets me. I don't think the camera's gonna let me. So like I said, it's the whole idea of the algorithm is to have a chain. So if this has a certain length and this is the distance, this is how much slack is left on the rope. So like since I call these chains, this is how much slack it gives. And you can just, like I said, you can keep getting smaller and smaller, and it kind of just ends up bending in the middle. So like I say, if a tentacle monster, wants to hit like a character, it has to go up and down right there. That's the end point. That's where I need to be to hit the person. So like I said, this will end up calculating the keyframe of where I want to, want the end point to be. And yeah, you can get as close as possible. And that's what it does. You can just move this around. See, there you go. Endpoint. And it basically, I'm using their idea to, and like this, like I said, it's that point, the way they do it with this arm. It's like really, it took me days to really figure this out, but it works pretty well. And that's not the only algorithm you can use for it. So that's a catenary curve. The next one I'm going to do is the circular curve. It was my first attempt, one of my first attempts. Before I ended up doing the catenary curve. The circular one, that one took me a while to get right, but it ends up creating a different effect. So the idea is I have two endpoints, and then I forget how I do. I have to look at the math, but I end up figuring out what a radius is. I forget what the radius is. I don't know if it's just half of this. I think that's what I do. I did probably just take the half length of this and then define this point. And then once I have that definition, I can then say how many joints do I need to do. And then I'm just creating all these points. Right? So that's so now I have that function I said that I can create circles in 3D space. So this way I'm able to use this to define all the targets. Now this doesn't work very well if I just do it as is, because the bones don't fit evenly. The catenary curve makes everything fit easily because it's based on the length of the chain. This circle is not based on the length of the chain. So once I have these circle points, I came up with a solution. They need a little help to figure out what to do, and it's the law of sines. Because I know, like I said, I know two lengths, I know an angle, and I need to figure out the length of the third triangle. So from the midpoint here, I know the length, and from here to here, I kind of know the length as well. That's A and that's B. This one, I don't know what the length is, but I know what the angle is. So this, from here to here, from this point to here, might actually be less or more than the length of the bone. So this is not the true spot where it needs to be. So by using the law of cosines, by knowing two lengths and one angle, and I think doing two different equations, I figure out the actual length of this leg. So by knowing the length of this leg, and I know the direction, I make this into a unit vector and then take that length and say, here it is. This is where, like if this is where the endpoint is, and this and this is how long the bone is supposed to be. This is how far it goes. And then I just apply that exact same concept to the next one. I just go around. Here's another triangle. I know the length between here and here, and I know the length of the bone. What is this? And I know the curve. I know the angle. And like I said, just repeat, rinse and repeat. And this actually does a pretty good job of laying things out for the most part. I think is once you reach a certain distance, it starts to fall apart. But if I want a nice reach around like thing, it works really well. Well, I've been talking for too long. Excuse me. All right, so that's the catenary curve. I mean, yeah, that. So now we're going to use the circular curve. So that's catenary. Now we have the circular curve. It follows a lot of the same ideas. We still grab the chain information. And so yeah, we get the point on the circle that we want. We got to calculate its length. We got the two lengths. Like I said, we need two lengths so we have an angle. Direction. And here's some of the math to I think the law of sines. Yeah, just like the dot product. I didn't write down the equation. But basically, using 1 to figure out the angle of B, then figure out the angle of C. Well, I already know what the angle of B is, so I'm just taking the dot product and then clamping it between 1 and 1 and using a cosine. That gives me the angle. Gives me this angle right here. The angle of B. So once I know angle of B, I can then use that to... This is the law of cosines. Oh, do I have the equation? No, I don't. But it's law of cosines, and it's the SSA algorithm, or the SSA equation. And it's pretty much just this. I guess A length times the sine of RB, the radius B divided by the length of A. And I just need to clamp it. And then I use the A sign to get the actual angle. And then once I have those two angles, I can subtract it from pi to get the angle A that I need. Because once you have two angles, you can solve the third angle by subtracting 180 degrees. But everything is in radians, so I just subtract from pi. Then I guess I do another law of sines to calculate the length. And I also, like I said, have the law of cosines that does work as well. But I think it's a much larger equation because it uses a square root. But the law of sines does a better job, so I don't have to deal with the square root. I just have to deal with two sines. So the law of sines can also get length as well. There's like tons of different versions of the law of sines. Like, it has a lot of equations of how to get this length and get that angle and things like that. So. Like I said, I spent like 3 or 4 days on this. And since I'm unemployed, I can actually spend entire days on this. Not just like 1 or 2 hours a night. So it took a lot of work, and I had a little help from Twitter. So thank you for everyone. For I think it was 2 people that suggested the law of sines. This is what helped me figure out this equation. I think someone even mentioned SSA is the one I need. And I found it, and I was able to apply it. And then at the end, I have a little push. I kind of do a little bit of inverse kinematics. If the distance is less than a certain amount, I kind of just nudge it closer to the point. It just makes things a lot better. So this algorithm is very involved. Like I said, this is one of my first attempts to try to get some kind of curvature. But it's like I said, I might be doing something. There might be simpler ways to go about this. But like I said, this is a novice trying to solve this. So take this as a grain of salt. This is not necessarily the best way, but this is all the math to kind of apply it. So once you have that, those are just, again, just targets that I apply to forward kinematics, and I can create a nice rounded curvature. And if you go to the top, let's say change the length a little bit. So then you get this, which is, like I said, I saw this, is like, this is great. I actually like, kind of like, if like, let's say if like the monster's here and there's like a pole and I want to reach around it, this will be a great inverse kinematics algorithm to actually apply, to actually get a keyframe where that's where I need the arm to be. So if I like a reach, like I said, I call it, this is my like reach around, my reach around algorithm. So I can have a tentacle reach around like some kind of like something. Let's see if I make it longer. I don't remember what happens when it gets longer. It's too long. I think it's 1.1. It's probably the refresh. So like I said, it's the, like I said, it was my first attempt, and when I saw this, it's like, ah, man. So it only works better when it's a little bit, the length is get closer to the half point of the amount of the chain is. Like I said, like this is a great one if you wanted more of a circular approach. Let's see what happens if I do 5, like really close together. Oh God, refresh. But here you go. So if I want to reach and grab something, the catenary curve is great. If I want to reach around something, the circular one works really well. Do I have anything else? And I don't want to go through. This one is just a sine wave. I really don't have to explain too much of this. It's just a sine wave. And I don't go too deep into this one. Like this kind of just I wanted to do at the very end. I was already kind of days of tired. Very simple. Yeah, I just plot a bunch of points and just move things and just make those targets on the sine wave. If I show you here, there you go. So I just plot those points on the sine wave and then just move them. Let's see if I make it a little bit longer. And like I said, it does a pretty good job. Like especially if I want to do a tentacle, like I want to kind of reach, and I want to do it in a kind of a wavy way. The sine wave works really well. I don't know what happens if I do 0. And that's a sine wave. I was thinking of another way to approach this is kind of like the circular one, where instead of using these sine wave positions, like I said, and everything's kind of a straight line, do it just like the circular. Just do 2 circles. Take the points and then have like a midpoint and have these connect at the midpoint. So do a half a circle here, half a circle here, and then apply that circle one. So this way I can actually move things a little bit closer to themselves. I was thinking about maybe doing it that way if I need to. If I want to maybe improve the accuracy or something, because like that works really well with the circle algorithm I put together to kind of just move everything into place. But like I said, with the sine wave, I didn't want to go too crazy with it. So if I do, let's see, do 2. Is 2 good? Yeah, that's a good one. And then like I said, I can move things around. So yeah, he's going that way, and there you go, sine wave. And like I said, this is all inverse kinematics, but I am just applying my own concepts to IK. Like I'm using curvature curve algorithms to help me figure out the targets for each point. And there's probably tons of other algorithms out there that we can use to actually get us there. But like I was kind of really focused on getting a tentacle working because it'd be fun. You know, that's kind of a fun thing to do. It's a simple thing to do before I start deciding doing. Because if I can do a tentacle really well, arms and legs should be a lot easier. So like I said, I spent a bunch of days trying to get this working just right, and then at the very end, I did arm and leg, which was the very simple approach. But this algorithm probably can work for two joints. Oh yeah, the only thing I did difference is that's right. It doesn't do a perfect job. The sine wave doesn't do a perfect job. I totally didn't even notice that. I totally forgot about that. Yeah, so that's the sine wave. That's how the sine wave ended up happening. But to make it a lot better, I just quickly apply the armature. Because this is a hack. Then I apply them. So this way, like I said, I need to do a better job of implementing, like how to apply these things without destroying the armature, without modifying the armature themselves. So, yeah, I totally forgot that the sine wave I cheated. That's why I said the second solution was to kind of do half circles. But a quick hacky version is that once I have the sine wave, make sure I calculate all the transforms. So this way, the transform hierarchy is there, and then apply it to I apply the backward. This is our regular inverse kinematics from the first video, just to nudge everything closer. So this is what it looks like with the sine wave by adding a second pass to it by using regular FABIK. Now it's a lot better. Now if I apply maybe one more time FABIK, if I do this might work. It might actually finally get everything just right. Refresh. Almost. It might probably, like I said, it might need 4, but it actually, like I said, it creates a nice curvature of it. And like all these things can be a mix and match. Like the FABIK is probably like our fallback solution. Like when we have all these curvatures, they're not perfect. Some of them are, like the catenary curve is actually pretty good. The circle one does a pretty decent job. You can always apply that too as well. And the sine wave isn't perfect, like the one I created anyway isn't perfect. But you can then use FABIK to kind of nudge everything and push it, like kind of straighten everything out to where they need to be. Yeah. So like I said, I just reapply, but like I'm not doing a good job of making it destructive. I need to figure out a solution to make sure my armatures aren't destructive. So I can just keep reapplying things, and then that's my keyframe. And then I can apply my keyframe to the armature. So right now I'm kind of destroying my armature. I need to maybe duplicate it and stuff. And that's it. There you go. I haven't, like I said, I haven't animated this yet, but animating, I've done videos in the past about how to animate armatures. So I'm really just focused on trying to get all this stuff working and building up that IK system so we can then start animating. Because like I said, the end goal is to kind of create like a keyframe that we can kind of then lerp, from keyframe to keyframe. So like I said, like for this example, if I need to move this tentacle and to say the hero is here, this is my endpoint. So wherever the tentacle is, like to say the tentacle is over here, I'm going to animate it to go into that pose. So it'll just transition, it'll lerp it, or I can create other keyframes. Create maybe 2 other keyframes or maybe some kind of wavy thing. So it's whatever. Sky's the limit how you want to animate it. It's like I said, I'm really focused on keyframes right now, not necessarily animating, because the animating part is easy. Like I've already done it before. I've already done it in a video. But yeah, this is advanced IK. This is my approach to it. Like I'm trying to my approach to figure out how he did it. Basically, he gives out clues, and that helps me go in a direction to kind of solve some of these problems. Like hopefully in the future, once I start building, having more IK riggy things, I can maybe I would love to have to rebuild this example, at least with the human leg, an animal leg, a tentacle, and in this one. If I can create those 4 legs and have them animate with the exact same animation information, then we're perfect. We're on the right track. That means we're like probably like halfway there, you know. So that's really the goal, is to get to this point where I can actually have one set of animations, apply it to different rigs of different types, and it just animates. And that's why I fell in love with this IK rigs from Ubisoft. But you know, it's not open source. I can't figure it out, so I have to figure it out for myself. And you guys are along for the ride as I figure this out. And of course, it's going to be open source. Anyone can use it. My hopes is that if I get this built and it works almost as good, I would love to start building a library of animations that people can just download and just apply and create new keyframes. Because the whole idea is that you have bits of animations and you can mix and match and create new animations out of it, and then add constraints to it, and then even change the animation even further. Like I said, the main information is a start and end point, and everything gets calculated. So you know, all you do is like a basic walking animation, and then you can apply it to any leg you want, or that animation could be applied to an arm, or you can apply it to a tail. You know, the sky's the limit, essentially. And that's another reason why I wanted to do a tentacle, because I want to do like tail animations. So you need to be able to kind of maybe do a sine wave or something. So yeah, it's a lot of stuff to do. This is going to be one of the most ambitious thing I've done so far when it comes to building a game engine, because this is something that took a professional with years of experience, God knows how long to do, and a team of people to help them. And I'm just an amateur trying to figure this out. So I think I'm doing pretty good so far. I still got a long ways to go before I can get something, this sample of his working for myself. But yeah, I'm tired. My throat's tired. So yeah, I hope you have fun. I hope you learned some stuff. It's like this one's very math heavy-ish. Like I said, I hope I managed to explain the math decently, and sorry for my bad drawings. Like I said, all the code's up there on GitHub. Feel free to take it apart, learn from it, port it over to whatever thing you want. Like this, you can probably port this over to like Unity. You know, I've seen like some IK rig systems on the Unity store, and there's like $90 to buy an IK rig system that they have, and I'm like sitting there thinking, man, I'm gonna build this for free. I'm gonna build this and give it out for free. You know, I should sell it, but you know what? I'd rather just have Patreon. So, just if you use it, and here's the thing: if you use this and you build an IK rig system and you're selling it on Unity or on any store like Unreal Engine store, if you take this and take my code and port it over, please, and you're making money off of me, please just donate at least $1. You know, at least give me something. You know, for all my hard work. It's like I'm not gonna stop anyone from using this code, but just common decency. If you're making money off of me, at least give me $1. You know, I'm not asking for a lot. You know, I wouldn't mind taking 20%, but $1 is fine. I'm good with $1. Like I said, I just need $300,000 and I'm buying a new house. So whatever. So I digress. See you guys in the next video, which we're going to deal with constraints. We're going to start constraining out. Whatchamacallit? We're going to start doing constraints with quaternions. Yeah, that was difficult. That was quite difficult to do. So that one's going to be another math heavy one. See you in the next video.